So we have seen two factors that the resistance depends on. One is length and the other is area. The third one is the material. You see, if you take an identical in shape wooden rod and another one, again like I said identical, okay, these are identical rods, one of steel, one of wood. Then do you think same current will flow in both of them if you connect it with the same battery? Obviously not, because wood is an insulator, steel is a conductor. Do you understand what I am saying? So the difference is due to material. So basically it's that different materials have different resistivity, or that different materials have different resistivity. Okay, so the third factor that resistance depends on is rho. That is, when we remove the proportionality, we have to write a constant. That constant is the resistivity. Did you understand? Yes. Okay, that constant is called the resistivity. Just one little note. So this is a very useful formula, of course. One little note. It said, in all these chapters, 1, 2, now 3, there are so many different quantities that we are studying. For example, in first chapter, electric field, Coulomb's constant, permittivity, second one, capacitance, etc. etc. So you may be asked dimensional formulas of all these. Okay, any one actually out of all the chapters, any one. Okay, in board exam typically. So what you should do is you should learn how to find dimensional formula of everything. For example, if you want to find dimensional formula of resistance, then you can go by V upon I is equal to R. But for that you need to know dimensions of voltage or potential. Is that clear? So like this, there are so many quantities for which you need to find dimensional formula. So make sure you know that. Okay? You will not be able to remember. There are so many. You will forget it eventually. એક ચેપ્ટરમાં જેટલી બધી આવે યાદ જ ન રહે એવા તો હજી 7th 8th ચેપ્ટર સુધી નવું નવું આવતું જ રહે. Okay, so please be careful with that. So similarly, you may be asked the dimensional formula of resistivity. You may be asked dimensional formula of resistivity also. Then you can find it if you know R dimensional formula. Okay or not? L તો આવડે, area આવડે, આ આવડતું હોય તો આ થઈ જાય. Got it? So you may have to do it indirectly. Anyway, the unit of resistivity will be ohm meter. Yes or no? Or not clear? Resistance unit is ohm. Everyone knows that? No doubt about it. Fine. Ohm, and then area, so meter square upon length meter. Did you understand?
Yes.
Area upon length. So if you cancel 1m, then you get ohm meter. Unit of resistivity is ohm meter. Got it? Sure. Per nahi ho, it's not ohm per meter. It is ohm meter. Fine. Okay. Fine. Now, so that's a little bit about the third factor, resistivity. So R depends on three things: rho, L, and A. Clear? Shall I erase everything off the board? Well, let's go over to the next. Now, having covered the basics of R and V and I and all that, let's define a new quantity called current density. Very easy. Current density. So first of all, the simpler version, part 1 of this problem. Current density is the current flowing through unit cross sectional area is called current density. So in magnitude form, in symbol of current density is J. It's a vector actually. J is equal to I by T. J is equal to I by T. Right? Current density, current flowing per unit area. Okay? Flowing through, flowing per the value. Current flowing per unit cross sectional area is called current density. What will be unit of this thing? Ampere meter square. Ampere per meter square. Got it? Okay? In anti-dimensional formula, right? Now, actually it's a vector. Direction of J vector is the same as direction of current. Direction of J vector is the same as direction of current. But this is frankly only to be used when current is uniformly distributed. Okay, this is only to be used if the current distribution is uniform. That means the current density is same everywhere. But what to do in a complicated? There would be more so like this, that J is equal to di by dA, where di is the small current flowing through a small area D. Did you understand? See, let me give you an example. Suppose there is a pipe like wire. Fill water to them. Let's say water is flowing in this pipe. Then water will be flowing everywhere, yes or no? Yes. But if you watch it from this side, if you watch it from this side, circle dekha, clear or not clear? Yes. Okay. So if you notice that from this area, small area, some amount of water is flowing per second. Then if the small amount of water flowing is di and the small area is dA, then over here how much will be the current density? Di by dA. Then it might be different at different places. Did you understand? It might be different at different places, right? So it's possible that from one point more current is flowing, but from the other point less current is flowing, and so on. So in general, if you have it this way, then the total current can be found by integration of this. By integration of J vector dot dA vector. Do you remember dA vector? Area vector 1, area vector, yes or no? IHJ. Okay, where you can mark any particular cross section. Where you can mark any particular cross section. Okay, then angle between J and dA, if it is theta, then that will be J dA cos theta. You do not use it very often, but sometimes yes. Okay, this is the basic version. This is the detailed. Fine.
Yeah. Current direction vector each direction હોય છે current
Sorry?
current direction કાં તો left હોય છે કાં તો right હોય છે. તો સર J ને vector કેમ કહેવાય? current.
So, why is current density of vector? Good question. It's actually that you only have to study about circuits. But the truth is that when we start talking about magnetic fields and electric field, their relations with each other, current density is actually a very important component or one important part of us, right? And when suppose charge is flowing in vacuum, normally we don't talk about current and all that, okay? And people write everything in form of current densities. You get what I'm saying? People write everything in form of current density. Now over there, the advantage of writing current density over current is that automatically if you write everything in form of current density, the expressions become simpler. Right? That is, see, you might say, sir, there is no need to define current density. I agree. There is absolutely no need to define current density. But then why is it there? It's because in many mathematical expressions, if you don't define current density, you will get things like this everywhere. I by A, I by A, I by A. For example, is there any need to define dipole moment? બધી જગ્યાએ 2aq લખો ને કોણ કહે છે તમને એને p લખો. You get what I'm saying? But because it appears everywhere, what do? We give it a name. Okay, so it becomes easy to talk about. or it's like nature is telling us that this is something important. Just like that, when we start talking about magnetic field and electric field and their relations, what happens is that everywhere instead of getting I by A, then it's better to write J. And exactly in those equations, the need is to get a vector over there. Okay, the need is to get a vector over there. You'll get some taste of it in the next chapter. And even though current is a scalar, we'll have to use its direction very often. Right? So, such things obviously occur in more advanced physics, right? When we try to relate everything. For example, like Maxwell's equations and all that. So, at that time, it's better to have a definition for this quantity. That's why it's written as current density. And like you said, why a vector? Same reason. Over there, in those equations, everything that we are getting is in form of, typically it's in the form of cross product. Let me tell you that. Obviously, you don't know the equations, but I can at least tell you that. It's in the form of cross product. So, it wouldn't make a lot of sense to write I upon A cross some other vector, for example. Because I upon A is a scalar. So, that's why we have defined something which is called a current density, that is I by A, but we treat it or we call it a vector. Make sense? Okay. Well then. Another reason that I can give you, which is going to point out why this would be wrong. For example, this is a pipe through which, listen to this carefully, this is a pipe through which in some unit time, let's say 3 liter water is flowing. So if I mark a cross section like this, an area, a circle like this, right? How much water would be flowing through that circle in 1 second? 3 liters. But instead of that, if I would mark a slant area, which is actually going to be an ellipse, pipe ma perpendicular cut karo the circle, if you make it slant, it will be an ellipse. Then do you realize that this area would be more than the circle's area? This is what's a straight line. I'm perpendicular draw karo from top to bottom. It's less in length, but I'm slant draw karo to more. Yes or no? Yes. So this would have more area. Then if I ask you, how much water is flowing through this shape in 1 second? Same as well. Do you agree? It will be 3 liters, not more. You know about it. It can't be more. Think about it. Because what this is, it's an imaginary shape. Yes or no? Correct? If water is flowing here, what is flowing here, what is flowing here, what is flowing here. You can see two volumes. One part is this, the other part is this. Yes or no? Both will have constant volume. Correct or not? So whatever amount is coming in from here should also go out from here, irrespective of this shape. So in both the cases, current or charge flowing through this area in some given time will be same. Okay, આ એરિયા તો વધારે છે, તો તમે આવી ડેફિનેશન યુઝ કરી શકશો. More area, current density would be less. But if you say that this is a uniform wire where current density is same everywhere, where current density is same everywhere, then there will be a contradiction. You'll have to give up on one of the things. I hope you realize that. I cannot give it. Flux samajh pade ne. If I say that there is uniform field and I take this area or this area, flux is same. Possible? Not possible. You have to give up on something. Is that clear? So that's what I'm saying. If the current density is same everywhere, then if you write J equal to I by A in scalar form, so આનો એરિયા વધારે છે, તો એનો શું કરંટ વધારે? No, not at all. Is that clear? Sure you get there? So current is same, there is no doubt about that. But there is also no doubt about the fact that area is also more. So what is one missing factor? The angle when you tilt it. When you tilt it. Make sense? Not very not so much. When you tilt it, the angle changes. So that's why it is better to write it in this form. કેવું થશે? as this will tilt, area vector will make angle more and more with the j vector. Yes or no?
Yes.
समझ पड़ेगा ना? As this will tilt, आम सही होता है ना? So as that angle will increase, the area will also increase, but then a into cos theta will remain same. That's why whether you take theta as 0 or you take theta as 30, the current flowing shall be same, with one exception, 90 degrees. When theta is 90, what will happen? बोलो आप जैसे है ना, तो ये मध्य current जाए, got it? Because then current will not flow through it. Make sense or not? Everyone understood this completely? So that is what is the entire thing, right? Nevertheless, so that's the reason actually we need this as a vector. Otherwise, if you just say j equal to I by A, it's going to create a problem like this. Fine? એટલે બે કેસ થોડા અલગ છે. અહીંયા કેવું હતું ખબર છે? If you tilt it, flux remains same? No. Flux will decrease. But here, the current should remain same. Here the current should remain same because as you tilt it, the area is increasing. Yes? No?
Yes.
As you tilt it, the area will increase. કારણ કે તે અહીંથી અહીંયા સુધી આવે. Like I said, પણ અહીંયા તો આટલું જ આવશે. So that's the difference. Okay. There is everything off the board? Yeah. To be very clear, when we go into deeper level physics of all this electric field and magnetic fields and all that, we have to write these equations in form of current tension. But in your book, they have never used. Your book presents always a simpler version where everything is written in form of current, right? Okay. But in higher level physics, definitely it's not. Okay, let's go to the next. Microscopic form of Ohm's law. Okay, take the easy derivation. See, originally the Ohm's law, when we write proportionality and remove the constant, remove the proportionality sign and get a constant, we get V equal to I. Okay, but now if we try to write this in form of current density, okay, and other such quantities, we will get a different form of Ohm. Right? Let's start. Here everything is measurable. What I mean is you can measure voltage, you can measure current from outside. We will convert it to something which you cannot measure. We will convert this equation to a form where all the quantities cannot be measured directly. You know, basically this is like a reverse proof of Ohm. Ohm never proved his law, to be very frank. He just proved that it's not theoretical. It was empirical law. You understand what is meaning of empirical? Done from experiments without knowing why. So he never knew why is V proportional to I. Let me be very clear about it. But he knew that this is right. Sure, just like we know pen falls down. Everyone knows pen falls down. A 2-year kid will also know pen falls down, but doesn't know why. Okay. So from this we get to another form which can serve like the basis of the theory. So let's start. First of all, I'll attack V. Suppose there is a conductor. And we assume, and it's actually a fair assumption, that inside a conductor, electric field is supposed uniform. That will be true as long as this is uniform. Okay, it's not true if this is not uniform. Anyway, so let's say this is a uniform conductor. Length of the conductor is L. Have you understood so far? Yes or no? You know how very kind.
Yes.
Electric field inside the conductor is uniform, E. Like this. Length of the conductor is L. Clear? Sure? If one point and another point, 2 points are taken, let's say X and Y, then the potential difference, Vx minus Vy. Okay, can you just tell me which point will be at what potential if it's drawn like this?
Yes.
X. Clear? Because electric field can go from high potential to low potential. And this is uniform. Then I can write it like this. Because we will go from y to x. I hope that makes sense. When I write vx minus vy, which is initial, which is final? Y is initial, x is final. So we are going from y to x. Clear or not? This step is clear. Minus actual formula શું છે યાદ છે કે નહીં તમને સેકન્ડ ચેપ્ટર ની actual formula શું નેગેટિવ integration e vector dot dr vector from initial point to final point. Yes or no?
Yes.
Easy બહુ યુઝ કરો ને એટલે જે actual હોય ને બધું છૂટી જાય. બરાબર ને? એવું થાય ને કોકવાર. Correct or not? Okay. So now what do we get here? Minus e delta r cos theta, and theta is 180 because we are going from y to x. Okay, and electric field is the opposite. So आप तो simplify करो એટલે into l આવે. એનો આવે. Delta r magnitude is l. E is e. Cos it 180 is minus 1, minus plus. Now this is called voltage. Yes or no? Yes or no?
Yes.
Please remember this. For a conductor, for a uniform conductor. For a uniform conductor with current actually. For a uniform conductor with current V equal to E to L. કેવું જોરદાર બનશે આપણું મૂવી એક ને એક ચીજ બે વાર આવે ફ્લેશબેક ઓકે ઓર નોટ ઓકે Never mind. This is not microscopic form of hope. No, go ahead. No, kehta. હવે અહીંથી તો ચાલુ કરો. So let's put V equal to EL. Okay, current. Let I be J into A. Simple case. J into A. Got that? કેનો ખબર પડી? ખબર પડી ને? J equal to I by I equal to J into A. And instead of resistors, let me write rho L by A. Okay, anything cancelled? A cancelled. બીજું કાંઈ? So E is equal to J into rho. You might remember rho J better. Okay. Is it fine? So E is rho into J, but we will not write it in this form actually. We will define a new quantity. Okay. We define conductivity. યાદ છે હીટ ટ્રાન્સફર માં આવતું હતું ને થર્મલ કંડક્ટિવિટી એ રીતે આ કઈ કંડક્ટિવિટી છે ઇલેક્ટ્રિકલ કંડક્ટિવિટી. We define electrical conductivity again property of material as what? Sigma. Sorry, we are out of symbols. Okay, હવે કેટલા ક્યાંથી સિમ્બોલ લાવવા? Sigma. Sigma here stands for electrical conductivity, surface charge density. No. Got it? So sigma is equal to 1 upon rho. What? Sigma is equal to delta के नॉट समझा. Sigma is equal to 1 upon rho. Now if I put sigma, rho's value here, therefore E is equal to J by sigma. Is that clear or not clear?
Yes.
Sigma is 1 upon rho. Rho is 1 upon sigma. Thank you. Then put it on that side. So J is equal to sigma E. This is called the microscopic form of hope. Use some because generally conductivity is constant or property of material. So you can write it like this. So જે બોલામાં I proportional to V. એવી રીતે J proportional to E. That's why it's called microscopic form of. Here any of the three quantities cannot be measured by instruments. You cannot measure how much is the electric field inside directly without measuring V. You also cannot measure what is J without measuring I. Is that clear? Right? So basically, if someone say when would Ohm's law be true, then I say if J is proportional to E, then Ohm's law would be true. If J is not proportional to E, then Ohm's law would not. Okay, yeah. You can also put this in vector form. Okay, in vector form, it will be J vector equal to sigma into E vector. Why is it like that? Let me see. If in some conductor, electric field is this way, then current will also be the same. Why? Think about it. Suppose our conductor is the free electron. Then do you realize that if electric field is right side, the free electrons will get forced towards the left side, correct or not?
Yes.
It means more free electrons will flow leftward. What if the free electrons will flow leftward? That's a negative charge flowing leftward. The direction of current will be right. Clear or not? So basically I and E in a metal are always in the same direction. Clear? But J is also in the same direction. Like that current density is always in direction of what? Current density is in direction of current. Is that okay? So that's why that means J and E vector are also in the same direction. How much padi gayi? That's why in vector form also relation remains the same. Got it? So this is called microscopic form of out derivation puts it 2 marks. Okay, this is one of the easiest. This is આ કઈ જ નહીં લખવાનો અહીંથી ચાલુ કરવાનું. V equal to IR, therefore this full. Got it? પણ એની સાથે સાથે sigma. What do you think are units of sigma? Reciprocal of resistivity. બરાબર ને? resistivity એટલે શું? ઓહમ મીટર. એવું હતું ને? તો unit of sigma શું આવે? Ohm inverse meter inverse. Yes or no? Sure. Ohm inverse નું એક નામ છે. Ohm. Not joking. This is real stuff. Ohm inverse is called mho. MHO. Ohm નું ઊંધું કર્યું, બીજું કઈ નથી કર્યું. Because we are running out of units basically. બીજું એક unit છે, it's called Siemens. Right? Siemens નામ સાંભળ્યું? એક બહુ મોટી ઇલેક્ટ્રિકલ ઇન્સ્ટ્રુમેન્ટ બનાવે ને એની કંપનીનું નામ SEIMENS કેવું? નેવર નો ના પડે સાંભળ્યું છે? Nevertheless, so this is mho per meter. Okay? Fine. So that's the unit of conductivity. ये जो dimensional formula पूछे तो आवड़ते हैं फाइंड करता है. प्रैक्टिस कर लेजो एक बार जो जो. हमारा टेस्ट डे में एक पूछा था dimensional formula. बोर्ड एकदम एक तो दो वर्ड से आवे आवे ने आवे. Okay. Fine, so ladies, everything here. Next, don't have a lot of time though. One is yellow side of the drift velocity. So, to understand what is drift velocity, it was actually the perfect time of the year, but unfortunately we don't have anything like a monsoon right now. Why? Because normally in monsoon the wind is quite strong, yes or no? Yes. Have you seen sometimes that birds are trying to fly in one direction, but wind carries them sideways? Have you noticed that? So like bird wants to go there, but because of wind it will drag and go here, but its beak will still remain in this direction. Up side ma fly થાય. Have you seen that or not? Okay, the bird doesn't turn, the bird remains like this, wants to go there, but wind carries it sideways. Fine, just like if you remember those problems, a boy trying to swim across a river Do you remember that? Everyone is flowing, so the boy gets dragged. Okay or not okay? Fine. So this topic is similar. Now to understand what's going on here, first of all, we draw a nice diagram. So let's say that these are ions that are left behind after their free electrons are roaming everywhere in the society. Did you understand what I'm drawing? This is basically the crystal lattice. What is it? Crystal lattice of the metal. Okay, so these are heavy ions. The figure is not to scale until the jagya, right? They are very close to each other. Nevertheless, now, if suppose some electron is over here at some point of time, free electron. Now you know everything is at some temperature. Obviously, all metals will be at some temperature, like Doyle temperature. So there will be random motion, yes or no? Depending on whether temperature is low or more or low or high, then the random motion will also be less or more. So this electron will not just sit there. It will be moving everywhere randomly here and there. So what will happen is occasionally, and I mean not occasionally, sorry, I take that word back, frequently it will collide with some ion and it will bounce off. It is very similar to, suppose there is a ball full of, a room full of balls, and let's say basketball, and someone hits a table tennis ball. Then what will happen? The table tennis ball will hit with one ball, it will go there, it will hit the other ball, it will go again in some other direction. Yes or no? Sure? Yes. Fine. Because that's actually the case, because the ions are quite heavy. This is what, for example, you take copper. Copper's atomic mass is about 63 gram per mole. And electron is only 1. Not even 1 in that way, but 1 by 1000. Because electron's mass is nearly 1 by 1800, that of a proton. So electrons are lighter. The ion but cannot kind of. Did you understand? The ions, they remain fixed. Everyone got that first of all? So it will hit here, it will go in some other direction, it might hit here, it might hit here, it might hit here. Everything is random. You get what I'm saying? It might move off randomly like this here and there. Any queries? It's possible that some of you might have a question. Isn't electron negative? If it comes close to a positive ion, wouldn't it capture it? Yes or no? But છોકરા બહુ તોફાન કરતા હોય તો ઘરે પાછા આવે તો બાર You get what I'm saying? Basically, metals don't have that much of attraction to their valence shell electrons. Correct or not? You get what I mean, right? આવે છે ને આવું કેમિસ્ટ્રીમાં કે દાદા આવતું. So what happens is that when there are lots of atoms together, all of them or most of them will give up 1 or 2 valence electrons, and those valence electrons become free electrons and they roam here and there. Even if this is attracted, it will capture it for a short time. I agree. If you take an ion and you give an electron to an ion, it will take it. But soon it will give it out. You understand that? No, sometimes. Why will it give it out? Because anyway it doesn't love it that much. It will let it go. Ionization energy of metals is very low. It will take it, of course, but that will not remain there for a long time. It will give it out. So like this, the electrons would be roaming around. Is this fine? પેલા કેમિસ્ટ્રી સમજાઈ ગયું બરાબર ને એટલે આવું થાય એટલું ખબર પડી ગઈ ને. It will not be captured. Even if it is captured, then very soon it will be ejected. Okay, like that. So this is what happens not just with one electron, but with all the free electrons. Can you imagine what kind of chaos is going on here? This is just one free electron. એવા કેટલા બધા હશે? અને બધા આમ. Similar to kinetic theory of gases. Fine. Okay. Here current will not flow. Why? because all the free electrons would be moving randomly. આમ જાય તો એક આમ જશે તો એક આમ જતો રહેશે. That's how all the flow of charge will get cancelled. Fine. But what would happen if there is an electric field? Let's say there is electric field everywhere. I'm just drawing it here to indicate. Let's say there is an electric field towards the right side. Then when this electron will try to move, what will happen? There will be a force on it. Yes or no? There will be a force. In which direction?
Right side.
Right side.
Left side.
It's an electron, isn't it? Electron is negative. So force on it will be towards the left side. Will that force be on only one electron? It will be on lot of electrons. Correct or not? Okay, in fact all the free electrons. But one little point that I want to make. Think of it like there are lots of trees. Okay, when a bird or when a crow, suppose, sits on the tree and there is no wind, then the bird can go from one tree to the next, this to next, and like that, so on. So, did you understand? But now, if there is wind, strong wind, let's say towards the left side, what will happen? The crow will get affected. Now, when will the crow get affected by the wind? When it is sitting on the tree, on the branch, or when it's trying to fly? Trying to fly? Sure? Absolutely clear? It will only get affected when it's trying to go from one point to the other. So what will happen is that the crow aimed that I will go in this direction, from this tree to that tree, for example. But instead of that, what will happen? The wind will drive it or push it in the other direction. Yes or no? Sure. But then let's say somehow it manages to sit on some other tree, not this tree. Let's say it starts flying like this. Okay, so it misses this tree but manages to sit on the other one, assuming there are lots of trees. Okay, now then it will try to fly to next one. What will happen? Once again, wind will apply force on it. Yes or no?
Yes.
Sure. So when will wind affect it? Only when it's trying to fly. Once it is with the tree, the effect of the previous effect of wind, all that will be removed. Yes or no? Got it? Sure. And then once again when it will try to fly, wind will show its effect. It will drag it. Correct?
Yes.
Correct or not correct?
Yes.
So remember this, please. I gave you this analogy after a lot of thinking, because this is exactly what happened. So what's going to happen here for this electron? Without electric field, it will follow this blue line. Yes or no?
Yes.
But with electric field, it applies a little bit of force on it. For example, then it goes till here. Make sense? જો આ blue જે છે ને એનાથી ઈધર વખતે થોડું left side જ રહેશે. Clear or not? Okay, I have drawn an exaggeration, but in reality it would be something like this. Gradually it would have started drifting. Towards the right side. Make sense?
Yes.
Compare the two, blue and black. સમજાણો કે ન સમજાણો? Yes, no.
Yes.
Blue would be without electric. It would be able to go from this to this, but black would be with electric, because electric field is continuously pushing it towards left side. So overall, see, if earlier random motion of all the electrons was getting cancelled out, but now all of them are going to get a little bit of push more and more towards the left side, then what will happen? Gradually the charges are drifting towards the left side. Yes or no?
Yes.
समझ पड़े कि नहीं? You know how to read. Gradually the charges are drifting towards the left side. Are they always moving towards left side? No. Like Palak asked earlier, will random motion stop if we give electric field? The answer is no. Random motion will still continue, but to that random motion a little bit of drift will be added. I can assume that crows will still fly. But where they are trying to go, instead of that, they'll end up going a little bit on the side. So gradually, if strong wind remains in one direction, then gradually the crows will start moving in that direction compared to where they are supposed to be. Get everything? Right? So draw this diagram. Okay, if you don't want to draw it, you see how the diagram is given in the book. Okay, the idea is of course this only, and we will continue with this the next step. Okay, we will derive a formula of drift velocity. That is with how much velocity is drift. Turn it off.